Hello everyone, a very good afternoon to good evening to all. Myself Vivekananda Naik. I am a PhD research scholar in the Department of Energy Science and Engineering, IIT Delhi. I welcome you all once again for this 10th introduction session on the course Solid State Physics, which is being flowed this semester by NPTEL with course code NOC24 PH0 July 2024 session. We will discuss a problem week 10 lectures of solid state physics course, that is covering the lectures, some of the lectures of 9th week and 10th week, which will cover the semiconductor physics and magnetic properties of matter. So let's start with the first question of today's session. Question says, question number 1, if the ratio of densities of charge carriers in pure silicon crystal at 27 degrees Celsius and 57 degrees Celsius is 0.125, then determine the energy gap of the semiconductor crystal. Option A 1.10, option B 0.75, option C 5.41, and option D 2.12. The question says the ratio of density of charge carriers in pure silicon is 0.125 at 27 degrees Celsius and 57 degrees Celsius. So since it is pure in 6 type of semiconductor, so of intrinsic charge carriers is 0.125 silicon, and we have to find energy to semiconductor crystal. Now we know the density of charge carriers is given by for intrinsic semiconductor equal to kBT divided by h square to the power 3 by 2 m star to the power 3 by 4 minus Eg by 2 kBT. So this is the expression. Now we will put the value temperature in this equation. We'll put two values of temperature and we'll take the ratio. And after calculating, we have only one unknown, because you see this E one unknown. If we cancel out from numerator, So if we solve it, then Ni at 27, Ni at cells equals to, now you see 2 pi kb by h cross square, it will cancel out. Now 27 degrees Celsius is equals to 300 Kelvin, and 57 degrees Celsius equals to 330 Kelvin. So if we put the values, then 300 by 330 to the power 3 by 2 cell minus Eg by 2 kBt. So here T will be 600, then for another temperature 2T will be 660. So it will be 600 kb plus Eg divided by 660 kb. That implies we know this value is given to us. So the ratio of 30 by 33 to the power 3 by 2 will be coming 0.867. Then exponential, if you take say it will be 11 plus 10 by 6600 kb, then it will be 0.867 exponential Eg by minus Eg by 6600 kV. So if you divide it 0.867 in the left hand side, 0.144 will be exponential minus Eg by kV. Taking ln on both sides, ln 0.144, but exponential will be cancelled out. It will be Eg by 6600 kb. Then Eg will be 6600 into kb is 1.38 into 10 to the power minus 23 into 1.94, which will give you 1.767 into 10 to the power minus 19 joule. So if you convert it into electron volt, we will divide it by 1.6 into 10 to the power minus 19. So it will come out to be 1.1 electron volt. This is the answer. Also, we know for pure semiconductor, band gap is 1.1 electron volt only. So, but here we learned about a method in which if two temperatures are given and the ratio of their intrinsic charge carrier is given, we can calculate what will be the band gap. If there is some semiconductor, we don't know the properties of that semiconductor, then this method can be used to calculate band energy. So the correct option will be option A, 0.10 electron volt. I hope this is clear to everyone. We will move to the next question. The question says, for an intrinsic semiconductor with energy gap of 0.7 electron volt, determine the position of the Fermi level at 400 Kelvin if the effective mass of hole is 5 times the effective mass of electron. The options are: option A 0.38308 below the conduction band, 0.205 below the conduction band, 0.105 electron volt below the conduction band, or 0.107 electron volt below the conduction band. These are the four options, and we know has band gap of 0.7 electron volt. So we know germanium has the band gap of 0.7 electron volt, and it's an intrinsic semiconductor also. But here we need to find out the position of the Fermi level at 400 Kelvin. We know the position of the Fermi level at absolute zero temperature is at the mid between the two. So at 0 degree, we have the Fermi level at 0.350 eV below the conduction band, or 0.35 eV below the valence band, because it is at the center of the energy gap. But here the temperature is given as 400 K, and the effective mass of hole is 5 times the effective mass of electrons. So we know for intrinsic semiconductor the Fermi level is given by EC plus EV by 2, 3 by 4 kBT ln mh star by me star. So you see, if T is 0 Kelvin, then the Fermi level will lie between valence band and conduction band, that is EC plus EP by 2. But here the temperature is non-zero, and the effective mass of hole is 5 times larger than the effective mass of electron. So I'll give you a few minutes to try this question, and then I will discuss what will be the correct answer. here if you see, all the options are given in terms of the label with respect to the conduction band. So what we can say, so 0.308, 0.205, 0.105 or 0.107, all these are below the conduction band. So we can take the LHS as EC minus EFI. So whatever the answer comes, it will be below the conduction band. So if you take minus on both sides, it will be minus EC by 2 minus EB by 2 plus EC. So it will be EC minus EB by 2. Also here plus 3 by 4 will become minus 3 by 4 kBT ln 5, because MH, the effective mass of hole, is 5 times the effective mass of electron. So the so conduction band minus valence band by 2 is nothing but the conduction band minus valence band by 2 is nothing but the energy gap. So this will be the energy gap, that is Eg by 2 minus 3 by 4 kBT ln mh star divided by me star. So EC minus EFI will be 0.7 electron volt. If you convert it to joule, it will be 1.6 into 10 to the power minus 19 by 2 minus 3 by 2, 33 by 4, 1.38 into 10 to the power minus 23 into T is 400 Kelvin into ln 5. ln 5 will be 1.6. So it will be 5.6 into 10 to the power 20 minus 20 minus 6.6 into 10 to the power minus 21. So it will be 0. If you arrange it, it will give you 4.94 into 10 to the power minus 20 joule, or if you convert it to electron volt, it will be 0.308 electron volt. So this is 5.6 minus 0.66 into 10 to the power 20. So 5.6 minus 0.66 is 4.94. So this is the correct answer, and correct option is again option A. I hope this is clear to everyone. Then question number 3. Determine the position of Fermi level in silicon at room temperature 300 K if its energy gap is 1.12 electron volt and the value of effective mass of electrons and holes are 1.1 into mass of electron and 5.5 into mass of electron respectively. So where m we know is the rest mass of electron only. So the question is pretty much similar, but here you see we need to find out for a different semiconductor and the temperature is also different. So if you see, we will again put the same formula and we will calculate the correct option. Options are 0.53 V, 0.43 V, 0.33 V or 0.23 V below the conduction level. So we will again convert the left hand side of equation to EC minus EFI and we will calculate. So it is a pretty similar question to the previous one. You should not face any problem, but try it and I will solve after a few minutes. So similar to the previous question, this EC minus EFI will be EZ divided by 2 minus 3 by 4 kBT ln 5, because here 1.5.5 m divided by 1.1 m is 5 only. So if you put all the values and calculate, you will get 8.96 into 10 to the power minus 20 minus 4.96 into 10 to the power minus 21. So it will be 8.96 minus 0.496 into 10 to the power minus 20. Then it will be 8.46 into 10 to the power minus 20 till joule. So converting into electron volt. 8.46 into 10 to the power minus 20 divided by 1.6 into 10 to the power minus 19. So it will be coming out roughly 0.53 electron volt. So the correct option is again option A, 0.53 electron volt. Now we'll move to the fourth question. The question says in an n-type semiconductor, the Fermi energy lies 0.45 eV below the conduction band at room temperature 300 K. If the concentration of donor atoms becomes 5 times, determine the new position of the semiconductor. So we can take the Boltzmann approximation that will be valid here for electron concentration in the conduction band. Again, the options are option A 0.41 eV below the conduction band, option B 0.51, option C 0.31, and option D 0.61 eV. All are below the conduction band. So we know for n-type semiconductor, According to Boltzmann's approximation, we can write N equals to Nc e to the power EF by kBt, and here Nc is the total available number of states at the conduction band. So you will use this formula and you will calculate what will be the new position of the Fermi level in the semiconductor. I'll give you a few minutes to try this question and then I will discuss how to calculate, how to approach this problem. So this is according to now for N-type semiconductor, the electron concentration can be equated to the concentration of donor atoms. We can write for N-type semiconductor. So we can write Nd equals to Nc exponential minus Ec minus Ef by kBt, where Nc is the effective number of density of states at the in conduction band. EC is the energy of the conduction level and EF is the energy of the Fermi level. And according to the question, the donor content concentration is increased to 5 times. So case 2, 5 Nd equals to Nc exponential minus Ec minus Ef prime by kBt. So the new Fermi level is Ef prime. So if you calculate, if you equate the two equations, then we will get 5 Nc e to the power minus Ec minus Ef by kBt equals to Nc exponential minus Ec minus Ef prime by kBt. So 1 by 5 will be exponential minus Ec minus Ef by kBt plus Ec minus Ef prime by kBt. So exponential Ef minus Ef prime by kBt will be equals to 1 by 5, taking ln Ef minus Ef prime will be minus ln 5 into kBt. Then so since all the equations, all the answers are given in terms of conduction band, so we will again convert it to Ec minus Ef prime. So Ec minus Ef prime is equals to Ec minus Ef minus kBt ln 5. So 0.45 1.38 into 10 to the power minus 23 into 300 into 1.6 into 10 to the power minus 19, sorry, divided by minus 19 into ln 5 is 1.6. So it will be 0.45 minus 0.04 EV. So 0.41 EV will be the correct answer. So you see 0.41 EV. So the option is again option A, 0.41 EV. Initially it was 0.45 EV. So the Fermi level has gone up slightly and now lies at 0.41 EV below the conduction band. So now we'll move to the question number 5. The question says in a p-type semiconductor, the Fermi level lies 0.3 electron volt above the valence band. If the concentration of the acceptor atom is tripled, determine the new position of the Fermi level at 300 Kelvin. Boltzmann approximation is also valid here for the whole concentration in the valence band. The options are 0.123 above the valence band. So this will be above the valence band. So in the side the equation, we will use a different expression since it is related to the valence band, position of the level corresponding to the valence band. Option B 0.727, option C 0.427, option D 0.5.2 eV above the valence band. So this question is pretty much similar to the previous one, but here only the donor atom is replaced by acceptor atoms, and the since we are talking about acceptor atom, so the semiconductor will be a p-type semiconductor. So I'll give a few minutes to try this question and then I will discuss what will be the correct option. So according to Goldman approximation, we may write the concentration in the valence band as P equals to NV minus EF minus EV by KBT, where NB is the effective density of states for holes in valence band, effective density of states for holes in valence band. It is the valence band energy, and EF is the Fermi level of the p-type semiconductor. Now similarly, for p-type semiconductor, this P can be equated to the concentration of donor atom So Na equals to Nb minus EF minus EB divided by KBT. So similarly for case 2, 3, it is given Na equals to Nb exponential minus EF prime minus EB by KBT. So if you calculate, you can easily get minus EF prime plus EF equals to KB T ln 3, then minus EF prime will be minus EF plus KBT ln 3, then EF prime will be EF minus KBT ln 3. Then since answers are given in terms of valence band, so it will be EF prime minus EV will be EF minus EV minus KBT ln 3, because in the question it is given the Fermi level lies 0.3 electron volt above the valence band. So this value will be 0.3 eV. So EF prime minus EV equals to EF minus EV. Sorry. So this place let me write once again. KBT ln 3. So it will be 0.3 minus 1.38 into 10 to the power minus 23 into 300 into ln 3 0.1.0986 divided by 1.6 into 10 to the power minus 19, then 0.3 minus 0.028 EV, 0.272 EV. So the Fermi level was lying 0.3 above the valence band. So it has gone down slightly, and now it has been placed at 0.272 kiloton volt above the valence band. So I hope this is clear to everyone. Now we'll move to the next question. Question number 6. Question says an electric field of 100 volt per meter is applied to a sample of n-type semiconductor whose Hall coefficient is minus 0.0125 meter cube per coulomb. Determine the current density in the sample assuming the electron mobility to be 0.35 meter square plus volt into second. Options are option A 2780, option B 2800 ampere per meter square, 2880 ampere per meter square, or 2980 ampere per meter square. So this coefficient is based on Hall effect. So we know the Hall coefficient of n-type semiconductor. It is given the sample is n-type semiconductor. So Hall coefficient we know R is equals to 1 by Ne. So the Hall coefficient for an n-type semiconductor RH will be 1 by Ne, where N is the concentration and E is the charge. So from here we can calculate the electron concentration, and then after calculating the electron concentration we know the conductivity. Conductivity is sigma. Sigma is since it is n-type semiconductor, it will be Ne mu n or mu E. So the value of mu E is also given, the electron mobility. Then from sigma we know the value of electric field, that is also given in the question. So we will calculate the current density J sigma E. E is given. So first from RH we will calculate N. From N we will calculate sigma. From sigma we will calculate J, that is the current density. So I request you to please solve on your own, and then I will discuss what will be the correct answer. So if we calculate RH is 1 by NE, that implies N is 1 by ERH, 1 by 1.6 into 10 to the power minus 19 into RH is 0.125. Then it is 5 into 10 to the power 20 per meter cube. Then sigma is Ne mu E. N is N is 5 into 10 to the power 20. Then 1.6 into 10 to the power minus 19 into mu is given 0.35, which will come out 28 ampere per volt into meter. Then the current density J will be sigma E. 28 into E is given 100, it will give you 2800 ampere per meter square. So it is I by A. So the correct option will be, so it is the correct answer. The correct option will be option B, 2800 ampere per meter square. Now question number 7. Question says, in a Hall experiment, a p-type crystal of length L equals to 0.2 centimeter, breadth 0.12 centimeter, and thickness 0.02 centimeter are considered along x-axis, y-axis, z-axis when the current current of 2.5 milliampere is applied along the x direction and the magnetic field of 0.5 Tesla is applied along the negative z direction. A Hall voltage of 1 millivolt is found to be developed. Calculate the charge carrier's concentration in the p-type crystal. Options are option A, option B 1.9 into 10 to the 20, option C 4.2 into 10 to the 25, and option D 6.5 into 10 to the 25. So since Hall voltage is developed, so we will first use the expression of Hall voltage, and then from that Hall voltage we will calculate the value of Hall coefficient, and then from Hall coefficient we will calculate the value of Hall concentration or the charge carrier concentration in p-type crystal. So I'll give you a few minutes to try this question, and then I will discuss how you will solve it and what will be the correct option. So the Hall voltage is given by VH equals to RH IB divided by D. So R is the Hall coefficient, I is the current, B is the magnetic field, and D is the thickness. So if you put the values, RH is the only unknown, so RH will be VH D by IB. So RH will be 10 to the power minus 3 into 0.02 into 10 to the power minus 2 divided by 2.5 into 10 to the power minus 3 into 0.5. It will be 1.6 10 to the power minus 4 meter cube per coulomb. Then we know RH is equals to 1 by EP for P type. So P will be 1 by ERH. So 1 by 1.6 into 10 to the power minus 19 into 1.6 into 10 to the power minus 4 equal to 3.9 into 10 to the power 22 per meter cube. So the correct option is option A. Now we'll move to the 8th question. The question says the Hall coefficient of a certain silicon specimen was to be found. The Hall coefficient given minus 7.4 into 10 to the power minus 5. The electrical conductivity of the charge carrier was found to be 200 ohm inverse meter inverse. Calculate the mobility of the charge carriers. The options are option A 0.015 meter square plus meter square by volt into second. Option B 0.147. Option C 1.623. Option D 0.262. So here again Hall coefficient is given. So since Hall coefficient is negative, so we know it is an N-type semiconductor. So RH will be minus 1 by Ne. So from this relation we can easily find out the concentration of electrons or the donor atoms. Then after finding the concentration we can use the equation of conductivity, because conductivity value is given, it is Ne mu E. So if you put all these values, mu is the only unknown, sigma is given to us, n we know, E we know, we can easily find out the value of the mobility of the charge carriers. So I'll give you a few minutes to try this question and then we will discuss what will be the correct answer. So if we calculate n equals to 1 by RHE, so 1 by 1.6 into 10 to the power minus 19 into 7.4 into 10 to the power minus 5. So n equals to 8.4 into 10 to the power 22 per meter cube, and since sigma is any mu e, so mu e will be sigma by any. Sigma is 200 divided by n is 8.4 into 10 to the power 22 into 1.6 into 10 to the power minus 19. That implies 0.015 meter square plus meter square divided by volt into second. So the correct option is again option A. Question number 9. Question says a semiconducting crystal of 12 mm long, 5 mm wide and 1 mm thick is placed in a magnetic field of 0.5 Tesla, which is perpendicular to the horizontal flat surface of the crystal. When a current of 20 milliampere flows lengthwise of the specimen, the Hall voltage across its width is found to be 45 microvolt. Find out the magnitude values of the Hall coefficient for the semiconductor. Options are option A 3.7 into 10 to the power 6, option B 4.5 into 10 to the power 6, option C 5.5 into 10 to the power 3, option D 6.5 into 10 to the power minus 6. So this is pretty much similar to the previous questions that we have solved. So I'll give you a few minutes to try this question. So here again we will, since the value of Hall voltage is given, so we will use the formula of Hall voltage. Then you see the current flows lengthwise, then the voltage developed is 45 microvolt. So we will use the value of D here as 1 mm, and we will calculate the value of Hall coefficient, which is pretty much straightforward. So I'll give you a few minutes to solve it and write but the correct option, and then I will discuss. So if we solve it, we know the whole voltage VH is given by RH IB divided by D. So RH will be BHD divided by IB. So BH is 45 into 10 to the power minus 6 into D is 1 mm 10 to the minus 3 meter. Then I is 20 milliampere, 20 into 10 to the power minus 3 into magnetic field is 0.5 Tesla. So the value of RH will be 4.5 into 10 to the power minus 6 meter cube or coulomb. This is the correct answer. Correct option is option B, 4.5 into 10 to the power 6. Then we will move to the next question. Question number 10. Question says an electromagnet has a solenoidal winding of 225 mm with a total of 900 turns. What is the magnetizing field near the center of the winding if the current is 0.8 ampere? Options are option A 3200 ampere per meter, option B 1600 ampere per meter, option C 1200 ampere per meter, and option D 1000 ampere per meter. So these are the four options. We need to find out the magnetization vector, the magnetizing field H near the center of the winding if the current is 0.8 amperes. So we know the H is given by Ni for a solenoidal winding, where N is the number of turns per unit length, number of turns per unit length. I is current. So here 900 turns is winded across 225 mm. So from that we can calculate the number of turns per unit length, and then from that if we put the value of current we can easily get the value of magnetizing field H. So I'll give you a few minutes to try this question, and then I will discuss what will be the correct option. So if we calculate, the number of turns per unit length will be total number of turns 900. So 225 mm मतलब 225 into 10 to the power minus 3. So it will be Ni, which is 900 divided by 225 into 10 to the power minus 3 into 0.8. It will be 3200 ampere per meter. So H is 3200 ampere per meter. The correct option is option A again. Question number 11. Question says a toroid of mean circumference 0.5 mm has 500 turns, each bearing a current of 0.15. Find the magnetization M of the core if it is filled with an iron of relative permeability 4800. So we know the magnetic field involving magnetization and magnetic intensity. And by mu 0 H plus M. Now we can calculate H like we did in the previous question. H will be Ni. Then if you calculate the magnetization vector, if we know the relative permeability of core is 4800, then we can calculate the value of M from the relation B by mu 0 minus H. So we will calculate first the value of H, and then we will calculate the value of B, and then from those two values only one unknown will be magnetization vector M. So we will calculate the correct answer. The options are option A 7.2 in 10 to the power 5, option B 8.7 in 10 to the power 6, option C 9.2 in 10 to the power 7, or option D 9.8 in 10 to the power 8. I hope this is clear to you. I'll give you a few minutes to solve this, and then I will discuss what will be the correct answer. So if we solve it, then we know the the magnetizing field H is Ni 500 0.5 into 1.5, sorry, 0.15, because in this question it is already given in 0.5 meter and the current is 0.15 ampere, so it will be 150 Henry per meter. Then again we know B is equals to mu H, where mu is mu r mu 0 absolute permeability, then H and mu r is given 4800, mu 0 is given 4 pi into 10 to the power minus 7. This is the value of absolute permittivity 0. Then B will be 4 pi into 10 to the power minus 7 into 800 into 150. It will be 0.9 Tesla. So since we have the value of B and H, so we can put the value of magnetization vector B by mu 0 minus H. It will be 4 pi into 10 to the power minus 7 into 4800 into 150 divided by 4 pi into 10 to the power minus 7 minus 150. It will be 7.198 into 10 to the power 5 ampere per meter. So M is 7.2 into 10 to the power 5 ampere per meter. The correct option is option A again, 7.2 into 10 to the power 5 ampere per meter. Then question number 12, which is the last question of today's introduction session. The question says a toroid is filled with iron specimen and specimen gets magnetized, and the value of magnetization is 7.5 into 10 to the power 5 ampere per meter. Find out the average magnetic moment for iron atom when the density of iron is 7850 kg per meter cube, where the atomic weight of iron is given. So if you see the options are option A 5.57 10 to the minus 25, 4.47 10 to the minus 27, 8.86 10 to the minus 24, 9.23 10 to the minus 31. So if you see, we know the density, atomic density we can calculate from the relation number density by Avogadro's number divided by mass. So N will be 7850 into 6.023 into 10 to the power 23 divided by mass is given as kg per meter, 55.85 gram per mole. So it will be, in terms of kg, it will be 55.85 into 10 to the power minus 3. So the number density will be 8.46 into 10 to the power 28 per meter cube. Then the average magnetic moment mu will be m by n. M is given 7.5 into 10 to the power 5 divided by 8.46 into 10 to the power 28. You calculate, it will be 8.86 into 10 to the power minus 24 ampere meter square. So since it is given average magnetic moment per iron atom, so due to average per iron atom, we divided the number density of iron atoms. So the correct option will be option C. So with this, I come to the end of today's interaction session. I hope the questions I explained here today will be beneficial for you to appear for the exams which will be occurring at the end of the current semester. I hope you are registering for the exam, which will be a great experience for you. So with this, I stop the today's interaction session. I thank you all for registering in this solid state physics course. So in the next interaction session, we will solve a few problems that will be based on week 11 lectures of the solid state physics course. Till then, good night.